Okay, so let's talk about constant acceleration. Imagine that you have a car that is accelerating at a rate of 1 meter per second per second. How fast is it going after 1 second? Let me repeat. It's accelerating at a rate of 1 meter per second per second. After 1 second, how fast is it going? You probably already know the answer. Uh, your answer would be, oops, 1 meter per second. And you're right, or at least mostly, because I have to put in something in here that wasn't in the question originally. I have to say that the car is speeding up from rest. We know that it's speeding up at a rate of 1 meter per second per second. But if we're not told how fast it's going at the beginning, we can't say how fast it's going after 1 second. Again, remember, acceleration doesn't tell you anything about motion. It only tells you about changes in motion. So I had to change this question so we knew what the motion was like before the question started. Or before we were given the information, before the acceleration was given, sorry, in order to fill that piece in. But now that we have that piece of information, we can probably say, okay, it's speeding up at a rate of 1 second per second. How fast is it going after 2 seconds? Well, after one, it was going one. After two, it's going two. And after three, it's going three. Great. That stuff you already knew. Constant acceleration and the meaning of something like meter per second is actually very clear in English. So remember that. But let's put it into some motion graphs so we can use this fairly easy idea so far to start also understanding something that tends to be a little bit harder for students, which is motion graphs. So I know that the acceleration is constant, which means I know that the acceleration has to always be a horizontal line because a constant value is always horizontal. A constant value is not a straight line, it's a horizontal line. If you had an increasing diagonal, that would not be constant, that would be increasing. So this is right at 1. And you can see, okay, there we go. We got it. Constant acceleration. Now, I could plot in here these points. And these points would do a great job at telling us 1, 2, oops, I didn't give myself enough height here. My mistake. Um, this is 1. This is 2. That's 3 up there. My mistake. But there's another way for me to go about getting this other than using that math. I can use the area under the curve. So the area here, if this is 1 second, 2 second, 3 seconds, I guess I should number all of those. This area here is 1, so that got me to 1. The area under this curve tells me my change in velocity. It went up by another 1, or a total, it went up from 0 to 2. And then here, it tells me it went up by another 1, or it went up by a total of 3. So that gives me my last point. And just like that, I have all of the information I need for my velocity versus time graph. We approached it 2 different ways. We got the exact same answer. That's a really good sign. For our next one, now I'm going to try and create a velocity versus time graph, or a position versus time graph using my velocity versus time graph. So for this, we're going to use the area under the curve. And I'm going to use this area here to plot my first point. I guess what I need to tell you is I need to fill in some more detail, just like I had to tell you from rest. I'll also say that it starts at 0. If we don't know where this car is starting, we don't know where to place our very first point. But as soon as I tell you that, now we can go. So from here, the area under the curve on this velocity versus time graph will tell me what my displacement was. So this would be 1/2 times 1 times 1 for a total of 1/2. And I should scale my axes real fast. 1, 2, 3, 4. There. Now I won't accidentally go off my graph again. So my very first point is going to be at 1/2 because that's the area right there as an area of 1/2. My next one, I can either do the total area to get my next point, or I could figure out how much added area there is. Let's do the total area first. So the total area would be 1/2 times 2 times 2 for a grand total of 2. If I did it a different way and I wanted to just find this area here, of this here, that would be 1/2. This is 1, which moves me up by 1.5 from where I was at 1 second. So at 1 second, I was at half, And you can see that then I, from here, had a displacement of half then 1. So either way you do it works. You can do it from the beginning and do the total area, or you could figure out where 1 point is and then do the next area and add that. Either way. And then our last one is going to be 1/2 times 3 times 3, which gets us all the way up to 4.5, which is right there. Then we can draw in our parabolic shape here. You can see that it has a curve to it. If I tried to match this to some kind of straight line, oops, that's terrible. If I tried to match that to some kind of a straight line, you can see that it definitely curves under the line. So this isn't a connect the dots. This is just recognizing, oh, this is actually better represented with a parabolic line than a straight line. So that gives us our all of our graphs. And we used areas under the curve to work from acceleration towards position. But let's quickly do a little bit with slope, because you can also use slope information to figure out a lot of this stuff. So using the velocity graph, let's just go back and make sure our acceleration graph's correct. Our slope along this part right here, I'm going up 1 for every 1 I go over. And you can see that if my slope is 1, I have a slope of 1. I also have a constant acceleration of 1. My slope on this graph is my acceleration. So if I always have a slope of 1, then I will always have a horizontal line at 1. Going to my next graph, this is a little bit trickier, and this is something that you wouldn't actually be expected to do algebraically, but you can do to some extent conceptually. So this is a curved line, so we can't find exact slopes. But what we could do is we could draw a best effort tangent line. That is to say, like a line that we think is roughly parallel to what the curve is at exactly this point. And once we do that, we could calculate what this slope would be approximately, and we would find that it is approximately 3. And that makes sense. Let's see, is it approximately 3? Yeah, that's not too bad. Like, look, I guess I should, it's probably like flaws in my drawing skills, but you can see that I'm going up 1 or 2 units, or yeah, down here it's like 2.5. So it's roughly 3, which jives with at time 3, I had a velocity of 3. So at time 3 on this graph, I should have a slope of 3. If I draw this slope here, it should be roughly 2. And then this one here should be roughly 1. So just like that, we can use some of our position information to figure out velocity graphs. But I'll tell you again, for curved lines, you're not expected to find exact slopes. The best thing to do is either to draw a tangent line or to do your best and pick 2 points that are along your parabola, connect to those, and then estimate what the slope would be along that area. So last thing that I want to mention, though, is I want to talk about curvature on this position versus time graph. So these graphs are going to curve one of 2 ways. They'll either curve upwards, and sometimes you'll only see part of it. You may only see like this part, or you may see a middle part. But if you see any curve that looks like a smiley face, an upwards parabola, then this is a slope that is constantly increasing. Because I'm going from a very negative slope. Sorry, the slope is not increasing, but it is increasing in a positive way. Because you can see, as I go around there, I'm going from very negative to less negative to less negative to 0 to more positive, more positive, more positive. So all of these have a positive acceleration because the slope is changing in a positive way. This one starts positive on the velocity graph, or on the position graph, which means we have positive velocity, but now I have less velocity, less velocity, less velocity, and then I have velocity that's starting to go negative. So this would be negative acceleration. Along this region here, everything on this side, you can see that it is an object that is slowing down. And everything on this side is an object that is speeding up. Okay, so last thing I want to talk about is I need to talk about freefall. And I probably should have just pre-written this part, but I didn't, so live with it. So let's talk about what free fall is. Free fall is any object that is in the air and being acted on only by the gravity from the earth. That means a hand's not touching it, you're not throwing it up, you're not catching it. It's only being acted on by the earth. And we also will generally assume that on the list of things not affecting it, that air resistance is small enough to be negligible. We're not saying air resistance never exists. We're just saying a lot of the time, if you're dropping a heavy enough compact object, at least while it's first speeding up, air resistance is negligible, meaning that we can safely ignore it when we're working our way through it. So if we have this object that has air resistance negligible, it's in free fall. Again, free fall means nothing's acting on it except for the force of gravity. Then its acceleration value will always be approximately 10 meters per second per second. I say approximately because the real value is 9.81 meters per second. The AP exam will expect you to use 9.8. The actual value is actually closer to 9.806. And in fact, there's no true value for the acceleration due to gravity because wherever you are on Earth, it is slightly different once you get out to the 10th or 11th decimal place. So it is acceptable in all these cases to simplify it. And the AP exam has said that it is an acceptable simplification to use 10 meters per second per second. I'll explain briefly why we're going to be using 10 instead of 9.8. Check it out. An object has been falling for 3 seconds. How much has its speed increased by? If we use 10 meters per second, we know it's increased by 30. If we use 9.81, that's right, you don't know how much it's increased by. You could use a calculator. You could maybe even work it out in your brain, but you can do this almost instantly. So get in the habit of doing the math in your head where you can, and using 10 because it just simplifies everything, and it's a lot easier to catch errors as well because they'll be a lot more glaring. So last time, free fall is an object that's in the air being acted on by no other object. And I want to emphasize that's true whether it's going up or it's going down. This object, as it's going upwards, is slowing down at a rate of 10 meters per second, which means its acceleration's that way. Then as it starts falling, it's accelerating at a rate of 10 meters per second, speeding up. But in both cases, it's accelerating at a value of 10 meters per second. The variable that represents free fall acceleration is always the lowercase letter g. So if you see g, you should know that it represents 10 meters per second, at least for the next few weeks. Thank you. I hope this helped, and I'll see you in class tomorrow.